Welcome back, students, to our Chemistry 1510 video notes. In this video, we're going to talk about electron configuration. We just finished a video about energy level diagrams that looked like these things over here. What we're going to do is we're going to take our energy level diagrams and we're going to condense them. And when we condense them, what we end up with is an electron configuration. So let's first look at this given electron configuration for neon. And then let's talk about how to use the energy level diagrams to write an electron configuration. So for neon's electron configuration, there's a couple of components that we need to look at. So first thing is that this beginning number is going to tell the shell, or remember the shell is also called the energy level. So this large number is energy level 1, energy level 2, energy level 3. Then the letter designation is going to be the subshell type, which is the type of orbital, right? So subshell type is the type of orbital. And then this numerical value here that is written as a superscript, this is telling you the number of electrons in that subshell. So all of these components come together to tell you how the electrons are arranged for that atom. So let's look at our energy level diagrams that we've drawn before for oxygen and potassium and then use those to write our electron configuration. So for oxygen, what we did was we put in our 8 electrons, starting with our lowest energy level, moving up to our next energy level, remembering that there's only 2 electrons allowed in each orbital, and that one has to be pointing up and one has to be pointing down. We call that spins paired. Then once you get to the 2p, where you have 3 degenerate orbitals, or called degenerate means the same energy, we half fill each of them, and then we come back and pair if needed. So oxygen has 8 electrons, and here I have drawn 8 electrons. So the energy level diagram really gives a little bit more information than the electron configuration, because it tells you if you have unpaired electrons here. And that's going to matter later on when you start seeing things like paramagnetic and diamagnetic, which are just fancy ways to say whether or not you have unpaired electrons or whether you have no unpaired electrons. So if we take this and we try and condense it into an electron configuration, here we have the 1s orbital. So we're going to write 1s. In that 1s orbital, we have 2 electrons. So we write a 2 superscript. Now that one is done. We go to 2s. In the 2s orbital, we also have 2 electrons. So we write a 2 superscript. In the 2p orbital, we have 1, 2, 3, 4 electrons. So we write a 4 superscript. So this would be the electron configuration for oxygen. Let's do the electron configuration for potassium as well. We'll start again with filling up our energy level diagram lowest first. Then we come to our 2p, which has degenerate, and we put 1 in each to spread them out, but because we have so many electrons, we have to come back and pair. Then we move up to our next highest energy level, fill that, come into 3p, fill 1 in each, and then come back and pair. I should be at 18 electrons right now, which makes this 19. So what we'll do for potassium is the same thing. We'll look at the energy level, the subshell that are given right here, the energy level and the subshell, and then we'll count how many electrons are present in that entire subshell and write that as a superscript. So 1s2, 2s2, 2p, 2, 4, 6 in that subshell. 3s2, 3p6, 4s1. So probably two things to talk about here real quick would be the difference between an orbital and a subshell. So when we look at our 2p, this 2p, when I consider this entire thing, this is a subshell. The p is a type of orbital, and in the 2p you have 3 of them. So the 3 2p orbitals make up the 2p subshell, and then individually there are 1, 2, 3 orbitals in your 2p subshell. So it's like the subshell is the umbrella, and the orbitals are what are under the umbrella. They're the smaller components. The other thing that's worth mentioning is you're probably noticing that I'm writing my arrows as half arrows like this. When you see these in textbooks or when you see them in homeworks, you might see them as a full arrowhead. The reason that I write a half arrowhead is because I'm an organic chemist by nature. In our organic chemistry, a half arrowhead means 1 single electron, whereas a full arrowhead means a pair of electrons. So really writing the half arrow is the way that's most correct. And I bet you that textbooks write the full arrowhead because it's easier to write the full arrowhead than it is to write the half arrow, and then we don't have to have this conversation. So let's talk some more about electron configurations and how we can come up with an electron configuration without drawing an energy level diagram first. So if we want to draw an electron configuration without having to draw an energy level diagram, then we need to start breaking up the periodic table. So here is my picture of the periodic table, and I've changed this periodic table from what you normally see. And what has happened here in your periodic table is we've taken it and we've broken it up into blocks. So in red, we call this the S block, where notice helium is over in the S block. In green, this is your D block. In blue, this is your P block. And in yellow, oh wow, my color stopped working. In orange, this is your F block. So, again, if we ignore the small human that is crying downstairs, what we're going to do is instead of having to draw an energy level diagram each time that we want to come up with an electron configuration, we're going to instead read this periodic table like it's a book. And so if we find oxygen on our periodic table, oxygen would be here. And what we'll do is we'll start at the upper left-hand corner right here, like you would in a book, and you would read the page from left to right. So you have 1s and then 2s. So you have 2 boxes in your 1s, which stand for your 2 electrons. So each box is an electron. Then you're done with that sentence. You come down here to the next sentence. You have 2s, and there's 2 boxes. So you have your 2 superscript here. Then you come across and you start your 2p, where you have 1, 2, 3, 4 until you get to oxygen. So you read your periodic table as if it's a book to come up with your 1s2, 2s2, and 2p4. That way, you don't have to write an energy level diagram each time. So let's do zinc then. So we've got zinc right here. And in order to figure out zinc's electron configuration, we're going to again read our periodic table like it's a book. We're going to start here at 1s, come across to finish our 1s. So each block, right? So this is a block and this is a block. So I guess each square, maybe so that we don't confuse blocks with individual elements, is going to be an electron. So we have 1s2. Now we come over and we fill in this part, which is 2s2. Then we come over, we fill in this part, which is 2p6. Then we come down to our next sentence, to 3s2. We fill up 3p6. We finish that sentence. We come down to the next row. We go to 4s2. And now something unusual happens. It's not a 4D that comes next. It's a 3D. So before, when we looked at energy level diagrams, I told you that what we would end up doing is coming up with a way where you don't have to memorize that energy level diagram. What we're going to do instead is have an idea of how this is set up so that now we can take our next step into our 3D and not have to memorize all the kind of weird differences, but we'll talk about how to remember that 4s comes first and then comes 3D when we discuss quantum numbers next. So we fill up the 3D because zinc's all the way here at the end, so that's 3D10. If we were to go one more and do gallium, which is right here, then we would continue with our 4p, and in our 4p we'd only go one box in, so that would be a 4p1. So this is how we're going to use our periodic table to help us figure out electron configurations without memorizing the energy level diagram. So this is a great place to stop. We're going to come back in another video to talk about quantum numbers. As always, thank you for your attention. This is Katoni signing out.